Okay, here we are in Unit 4, and we're going to look at Lecture 1, which is more fun with hypothesis testing and confidence intervals. So pretty much you're going to have the same ideas, just different models. We're going to look at comparing two proportions instead of just one, and we're going to look at what model you use if you want to look at quantitative data like the mean. Okay, let's get to the next slide. Comparisons between two percentages are much more common than questions about isolated percentages. So you already looked at the one prop, z-test, and z-interval. Now we're going to look at two proportions, and they're more interesting. We often want to know how two groups differ, whether a treatment is better than a placebo control, or whether this year's results are better than last year's. In order to examine the difference between two proportions, we need another rule, and the standard deviation of the sampling distribution model for the difference between two proportions. Recall that the standard deviations don't add, but variances do. In fact, the variance of the sum or difference of two independent random quantities is the sum of their individual variances. So we want to figure out, okay, what's the difference between these two proportions? Well, it is a normal model. The difference between them is centered at the difference between the two proportions. But the standard deviation, that measure is going to be PQ over N plus PQ over N, well, PQ over N squared plus PQ over N squared, those variances, and then you take the square root of that. So the sampling distribution model for the difference between two proportions, provided that the sample values are independent, the samples are independent, and the sample sizes are large enough, if you want to look at the difference between two proportions, that's going to be a normal model where the mean is P1 minus P2, and the standard deviation, this is new, is P1 Q1 divided by N1 plus P2 Q2 divided by N2. All right, and so when the conditions are met, we are ready to find the confidence interval for the difference of two proportions. And the confidence interval is just going to be the difference between the two sample proportions plus or minus z star, which we already know about, times the standard error. So this is your margin of error, and the way that you compute the standard error is to do P1 Q1 divided by N1 plus P2 Q2 divided by N2. And so it's easy to get an Excel spreadsheet that will help you do that, which I have created for you, or you can create on your own. Okay, so let's look at it. What you're going to do is you're going to input the function, input either the percent or the part out of total, however it's given to you, and then Q1 would just be calculated as 1 minus whatever you have in there. And the sample size is N1 for that first proportion. And then in P2, you're going to put whatever, either the percent or the decimal for the second proportion that you're looking at. And then Q2 is just going to be 1 minus what you had in there. N2 is going to be the sample size for the second proportion, and then whatever confidence level you want. So your Z star is just, we talked about this already, it's going to be like whatever the percentage is, whatever the inverse, the Z value is for the given confidence level. And your standard error is going to be the square root of P1 times Q1, so that's why that's F3 times F4 divided by N1, which is F5, and then plus P2 times Q2 divided by N2. Now your margin of error is just going to be your Z star times your standard error, so that's why it's F10 times F11. And then your lower confidence level is just going to be, all right, let's find the difference in the two proportions, and then we'll subtract the margin of error. So your upper is going to be the difference in the two proportions, and we add the margin of error. And in a minute, went too fast. In a minute, we'll talk about the hypothesis testing formula. What's interesting about the hypothesis testing formula, and I don't have it all in here, is that you have to, you're going to pool your variances. We'll look at that in a little bit, though. Okay, so let's look at an example. In 1991, researchers at the National Cancer Institute released the results of a study that investigated the effect of weed-killing herbicides on house pets. They looked at 827 dogs from homes where a herbicide was used on a regular basis, and they found that there were 473 malignant lymphomas in those pets. But only 19 were found in homes, the 130 dogs that they looked at from homes where no herbicides were used. And so we want to look at what the difference is in the two proportions. And in this case, we just want to use the Excel program to find the standard error of the difference. All right, well, let's do that. And then we also want to find a 95% confidence interval. Okay, so how did I get this 0.5179? What I did is I put an equal sign, and I'll do it with you live. I'm going to put an equal sign. Oh, okay, let me take a minute to look at this spreadsheet. When you're looking at this spreadsheet, let me get it to fit in here. Down at the bottom, I have it so that there are separate sheets, one for the 1 and 2 proportion, one for the 1 sample mean, and then another sheet for the 2 sample mean, which we're going to look at in a later unit. But the 1 and 2 sample proportion are on the same sheet. So this is the 1 proportion confidence interval, but we're interested in the 2 proportions. So you want to move over to this one. Okay, and so our P1 value was equal to the first number that we were looking at, which was for those dogs, what was it? We had 473 out of 827. So 473 divided by 827. And we put the equal sign in there. So then it automatically computes the Q1, and then the N1 is the sample size, which was 827. And then P2 was the 19, so you'll do equals 19 out of 130. So sometimes on the online homework, they'll give you the percentage, and sometimes you have to calculate it. And the N2 is 130. And we want a 95% confidence interval. So what we see is we have 0.356 to 0.495, and if you made those decimals, that would be, percents, be 35.6 to 49.5, and that's the difference. It's quite dramatic how much higher percentage there is in the homes that use herbicides versus the homes that don't, and it can be as much as as little as 35.6 percentage more to as much as 49.5. That's kind of how you can read that information. And then the question was to calculate the standard error, which it did it for you right there. You could have done it by hand if you did the square root of P1 times Q1 divided by N1 plus P2 times Q2 divided by N2. So that's that value, 0.035. All right, so this one's your standard error, and then this confidence interval says we are 95% confident based on the data that the proportion of pets with malignant lymphoma in homes where the herbicides are used is between 35.6% and 49.5% higher than the proportion of pets with lymphoma in homes where no pesticides are used. So the 2 proportion z-test is similar to the 2 proportion z-interval. The conditions for the 2 proportion z-test are the same for the 2 proportion z-interval. But your hypothesis that you're testing, the null hypothesis, is that P1 and P2 are equal. And we have an Excel program. I wrote the program for you that will help you compute this. What's interesting is that we use a technique called pooling the data to find the standard error, because we're assuming that the proportions are equal and thus would have equal variance. And you can read more about that in chapter 22 of your text. But I went ahead and when I wrote the Excel program, I assumed that you have pooled variances. So let's look at an example. It's widely believed that regular mammogram screening may detect breast cancer early, resulting in fewer deaths from that disease. One study that was investigated this issue over a period of 18 years was published during the 1970s. Among 30,565 women who had never had mammograms, 196 died of breast cancer, while only 153 of 30,131 women who had undergone screening died of breast cancer. And the question is, do these results support the effectiveness of regular mammograms in preventing deaths from breast cancer? Let's conduct a hypothesis test. Our null hypothesis is that the 2 proportions are equal, or that the difference between them is 0. So the proportion of deaths from breast cancer is the same, that should be of women who never had a mammogram as for women who had had a mammogram. And the alternative hypothesis is that the percentage of deaths for women who had never had one is greater than for women who had had one. So the proportion of deaths from breast cancer is greater for women who've never had one as for women who had one. All right, we need the random, in our model, we need to check our conditions. So we have the randomization condition. We have to assume that the women are representative of all women. The 10% condition, certainly 30,565 and 30,131 are both less than 10% of all women. And the groups were chosen independently, so we have our independent sample condition. The success failure condition, you want to look at N1, P1, N1, Q1, N2, P2, and N2, Q2. Those are all greater than 10, so your sample sizes are large enough. And so then we make the statement, we say, since the conditions have been satisfied, we will model the sampling distribution of the difference in the proportions with a normal model. And I'm going to go ahead and in the mechanics, I'm going to let my computer or Excel do most of the work. To get P1, I'm going to do, this is from the dog one, so I'm going to have to fix that. I'll fix that on your sheet, but sorry about that. I should have input the numbers, which I'm sure that I did here. I'm going to input these. Let's go ahead and do it in here. The percentages from the women. So sorry about that. Let me go back and get those numbers, and we'll input them into our spreadsheet. So they are 196 out of 30,565. That's your P1. So we'll do equals, and here we'll do equals 196 out of 30,565. And then on N1, that's the 30,565. And then for P2, we have 153 out of 30,131. So we'll do equals 153 out of, so divided by 30,131. So you need to change your sample size to be 30,131. Okay, and you can leave your confidence interval there. And the null hypothesis, you don't have to input this value because you're just going to expect that it will be equal to 0. And so here's your p-values and such that we get. So let's see if that is consistent with what I got on the spreadsheet. Hopefully it is. Yes. All right, so the numbers that I just worked in the live spreadsheet seem to be matching the numbers that I have on the on the PowerPoint. And what you can say then here is look at these numbers right here. We were wondering if P1 was greater than P2, which would mean that the difference would be greater than 0. So you're going to select this one right here, and it says 0.0148. And that is a very small p-value. And with a p-value this low, we reject the null hypothesis. There is strong evidence that the proportion of breast cancer deaths for women who have never had a mammogram is greater than the proportion of deaths for breast cancer for women breast cancer for women who have underwent the screening. Okay, and so that it does sort of go along with our instincts. Now, these are extremely small percentages, obviously, of death because, in a large percentage of women, it's going to be a large sample size, you're going to have a very small percentage of women that are going to die from breast cancer to begin with. So it's kind of tricky. Another thing you might look at is the lower confidence interval and the upper confidence interval. While they are small, they are both positive. And the only way that you would fail to reject the null hypothesis is if your lower confidence interval was negative and your upper confidence interval was positive, because then your confidence interval would contain 0, which would mean you couldn't eliminate 0 as a possible value for the difference between the proportions, which would mean that you would have to accept, or you'd have to fail to reject your null hypothesis. You wouldn't have evidence to suggest a difference from the null. But in this case we do, because our confidence interval, our lower and our upper, are both positive, which means there is a slightly higher percentage in women who have not undergone screenings. Okay, now if you're dealing with quantitative data, we want to try and figure out what we're going to do. So now that we know how to create confidence intervals and test hypotheses about proportions, it'd be nice to do the same thing for means. Just as we did before, we will base our confidence intervals on our hypothesis tests and our hypothesis tests on a sampling distribution model. So, but the thing is, we can't quite use the normal model. The central limit theorem told us that the sampling distribution model for means is normal with a mean of mu and a standard deviation of, oops, I lost it. It was sigma over the square root of n. All we need is a random sample of quantitative data and the true population standard deviation. And that's the problem. Proportions have a link between the proportion value and the standard deviation of the sample proportion, but this is not the case with means. Knowing the sample mean tells us nothing about the standard deviation of the sampling distribution. We'll do the best we can, and we estimate the population parameter with the sample statistic S. So, you take your data and you find the standard deviation, and our resulting standard error is S divided by the square root of n. But you have extra variation in our standard deviation and error from S, which is the sample standard deviation. We need to allow for the extra variation so that it does not mess up the margin of error and the p-value, especially for a small sample. So we had, and the shape of the sampling model changes. The model is no longer normal. So what is the sampling model? Well, an engineer named William Gossett, who was in charge of quality control at a brewery in Dublin. You can imagine he couldn't sample too many beers to see if they were okay, otherwise he would not be able to make good choices. So he had small sample sizes, and he realized that when he was doing quality control on small sample sizes, the normal model wasn't exactly working out for him. And he took some time off and he studied statistics, and he found out that the sampling model that would work would be called what he called the student T's model. And he didn't call it the Gossett model because the brewery was very protective of all their recipes and everything, and they didn't want anyone to know that one of their engineers was, coming up with this grand statistical model that may lend trade secrets out to the other breweries. So it became known as the student T's model. Normally it would be the Gossett model, but because he couldn't put his name on it, it's called the student T model. The student T model is from a whole family of they form a whole family of related distributions that depend on a parameter known as the degrees of freedom. And that basically is the sample size. The larger the sample size, the more the T model looks normal. But when you have a small sample size, it's still kind of unimodal and symmetric. It just has wider, more area in the tails. So when Gossett corrected the model for extra uncertainty, the margin of error got bigger. So your confidence intervals are going to be just a little bit wider, and your p-values are going to be just a little bit larger than they were using the normal model. By using the T model, you've compensated for the extra variability in precisely the right way. Student T models are unimodal, symmetric, and bell-shaped, just like the normal, but T models with only a few degrees of freedom have much fatter tails than the normal. And the degrees of freedom, it means the sample size -1 for this basic model that we're looking at. So your normal model is the dotted one. Gossett T, when you only have 2 degrees of freedom, which means you only have 3 items in your sample, is see how there's more area under, like this is within 2 standard deviations, there's more area. So as for the degrees of freedom, but as you have more data values, the T model starts to look more and more like the normal model. And with infinite degrees of freedom, the T model is exactly the normal model. So you don't have to worry about this too much because we're going to have Excel help us calculate these values. But so a practical sampling distribution model for means is when certain assumptions and conditions are met, the standardized sample mean, instead of a Z, you have a T, which is data value minus the mean divided by the standard error, follows a student T's model with n-1 degrees of freedom, and we estimate the standard error with the sample standard deviation divided by the square root of the sample size. And so the T interval, one sample T interval, looks very similar to the Z interval that we used, where you're using the population mean or the sample mean that you got, plus or minus, instead of a Z star, you have a T star, and this n-1 means that it depends on the degrees of freedom for your particular sample size and then your confidence level. And it's not such a horrible thing to do because the computer can do all this for us. And then your standard error is just your sample standard deviation divided by the square root of n. When you're doing a hypothesis test, you're going to test the hypothesis that mu is equal to mu naught, some hypothesized value, and you get the statistic where you do your sample value minus mu naught, which is your hypothesized value, divided by the standard error, and then you see what, get a p-value based on that to find out that number. So, and of course, I've written the Excel program to help you do this. And we have some assumptions. You have an independence assumption. You need to make sure that the data array is from a random sample, and you have a 10% condition. You want to make sure that the sample itself is no more than 10% of the population. You need to make sure that your sample is normal. If you have a small sample size, it's really important that it looks pretty normal. For moderate sample sizes, between 15 or 40 or so, the T works as well as the data are unimodal and reasonably symmetric. Okay, and here are the formulas. Now, it's important for you guys to understand that this T dot inverse command and these T dot distribution dot right and T dot distribution, these commands are only in Excel 2010. So if you don't have Excel 2010, you're probably going to need to get on a computer that has that, so you'll be able to use this worksheet. So in the Excel program, you're going to just input your mean, the sample mean and the sample standard deviation, and the sample size and whatever confidence level you want, and then this calculation will get you the values. It'll give you the T star, and then the standard error is just the sample standard deviation error, so that's B4 divided by the square root of n, so that's why that's Bn. And then to get the margin of error, you're just going to take your T star value and multiply it by your standard error, so that's B9 times B8. And then to get the lower confidence value, you're going to take your sample value, which is your sample mean, which is B3, and subtract the margin of error, and then add the margin of error. And then if you're doing a hypothesis test, you enter what the null value is, and the z-score, in this case the t-score is going to be data value minus mean divided by standard deviation, and you're going to then, or standard error, if it's greater than, you want the area to the right on the t-distribution. If it's less than, you want the area to the left, which is the t-distribution gives that. And if it's not equal, you want to double either the area to the right or the left, depending on how the null compares to your sample mean. Okay, so in this formula, if you look in the Excel spreadsheet that I gave you, what you want to do is, it's the second sheet. This is the first sheet, has the 1 and 2 proportions. The second sheet, if you click on it, has the one sample T for means. So I've already done the calculations for you. Let's do an example. A nutrition laboratory tests 40 reduced sodium hot dogs, finding the mean sodium content is 310 with a standard deviation of 36. We want to find a 95% confidence interval for the mean sodium content of this brand of hot dog. So we'll go to our Excel spreadsheet and we'll input the information. The sample mean is 310. The sample standard deviation is 36. And we tested 40 hot dogs, and we wanted a 95% confidence interval, so 0.95. And then it's going to calculate everything else for us. The degrees of freedom is the n-1 and such. And let's see if our numbers are similar to what they got here. Hopefully they are. So between 298.48 and 321.51. And that's the same numbers. So that's your lower confidence and that's your upper confidence. So in the context of the problem, we would say with 95% confidence, the mean sodium content is in these reduced sodium hot dogs is between 298.5 milligrams and 321.5 milligrams based on this sample. Okay, let's look at another example. This one's kind of fun because we actually get to enter the data into Excel and calculate the mean and standard deviation. So it says Bjork Larson was trying to decide whether to use a new racing wax for cross-country skis. He decided that the wax would be worth the price if he could average less than 55 seconds on a course he knew well. So he planned to test the wax by racing on the course 8 times. His eight race times were those numbers. And the question is, should he buy the wax? And we want to explain it. So we're going to conduct a hypothesis test and support our conclusion with a confidence interval. So our null hypothesis is always that it's just equal to 55 seconds. And then the alternative, he'll purchase the new wax if it's less than 55 seconds. We have an independence assumption. And this one's a little bit tricky because, you know, I don't know if you guys have ever skied, but it seems like if you ski down the same course over and over again, it might get more slick. So I don't know that it would be totally random, but we'll just say that it is. If we look at a histogram of the times, we see that it's unimodal and roughly symmetric. Since the conditions for inference are satisfied, we can model the sampling distribution of mean times with a student T model. Okay, so, and I'm just going to, what you do is you enter the data. Just go ahead off to the side, go ahead and put the data in and then calculate the mean and the standard deviation. And then you can, right in here, you can just say equals, like in this case, it was D12, and then this one's going to be equal to D13. And then the sample size was 8, and the confidence level that they want, a good one would be 0.95. And then if you're doing a hypothesis test, the null value that you're going to enter was, in this case, 55 seconds. And your, oh, I'm sorry. It just went crazy on me, didn't it? My computer is very sensitive when I'm recording. I'll just take a break for a second. I'm sorry about that. Okay, so the p-value for the less than, notice we put the 55 in for H naught, is at 0.2347. So that's like 23.47%. So remember, the p-value is the probability that your data could come from a place where the null hypothesis is true. So there's a 23.47% chance that your data came from a place where the null hypothesis is true, where it's in the mean time is really 55 seconds. Well, that's a very high p-value. That's a pretty good chance. So you do not have enough evidence to suggest that the mean ski time is less than 55 seconds. And you say that he should not buy the ski wax. Now notice that the confidence interval of 47.22 to 58.97, that contains the hypothesized value of 55. And so again, that lends support to the hypothesis, the null hypothesis, which is why you can't reject it. So you really don't have evidence to say there's a difference from the null. Okay, now the last kind of idea here is the formula that you would use for finding the sample size when you're working with the mean. And it turns out that you just take whatever your confidence level that you want, Z star, whether it's 99, 98, 95, or 90, and multiply by the standard deviation and divide by the square root of the margin of error and square it, and then just round that to the nearest integer, and that's going to be your sample size estimation. So you have a couple homework problems where they ask you what would be a good sample size for a particular margin of error and such. Cautions about the t-test is you want to make sure that the data is nearly normal. You want to be careful for skewed data. You want to watch out for bias. You remember when we talked about did you ask if people were in favor of a smoking ordinance outside a bar? You have to be careful with that kind of bias. You want to make sure the data are independent. So you're going to check for the random sample and 10% condition. And you want to make sure that the data are from appropriately randomized sample. Be careful how you interpret your confidence interval. Many statements that sound tempting are in fact misinterpretations of a confidence interval for the mean. The confidence interval is about the mean of the population, not about the means of the samples, individuals in samples, or individuals in the population. So just kind of be careful with that. So we see now that statistical inference for mean relies on the same concepts as for proportions, and only the mechanics has changed, but I've already given you the Excel spreadsheet to help you do that. So the reasoning of inference and the need to verify that the appropriate assumptions are met and the proper interpretation of confidence intervals and p-values all remain the same regardless of whether we're investigating means or proportions. And the next lecture we're going to look at comparing two means either with independent groups or matched groups, and we're going to see that we're going to use the same sort of logic, and that's why on your Excel spreadsheet there's actually a bottom one here for two samples. That's what we're going to do in the second lecture for Unit 4. Okay, and I think you're about ready to start your homework.